Imagine boarding a flight and noticing something different. The windows are larger, the cabin feels more spacious, and the hum of the engines is quieter than you remember. You might not realize it, but you're likely on a Boeing 787 Dreamliner, a plane that has reshaped the airline industry. This isn't just another airliner. It's the result of a $30 billion gamble by Boeing, a bold move to redefine how planes are built and how we travel. The days of massive, lumbering giants like the 850-passenger Airbus A380 or the 660-passenger Boeing 747 are fading. These behemoths, once symbols of aviation's ambition, are being outmaneuvered by a new breed of aircraft designed for efficiency, comfort, and versatility. The 787 is at the heart of this revolution, and it's changing air travel in ways that directly benefit you, the passenger. Gone are the days when connecting flights were the norm for long-haul journeys. Your local airport now likely offers direct flights to far-off destinations at prices that feel surprisingly affordable. This shift isn't accidental, it's the result of the 787's innovative design, which allows airlines to operate long-range routes profitably with smaller, more efficient planes. The 787 isn't just a technological marvel. It's a game-changer that has made air travel more accessible and comfortable. Let's dive into what makes this aircraft so special, from its groundbreaking materials to its cutting-edge systems, and explore how it's redefining the skies. At the core of the 787's innovation is its use of composite materials, particularly carbon fiber reinforced plastics, which make up 55% of the plane by weight. This is a radical departure from traditional aircraft, which rely heavily on aluminum. The 787 was the first commercial airliner to be primarily constructed from composites, a trend later followed by the Airbus A350X WB in 2015. Composites are a combination of materials carbon fiber, made of thousands of tiny, strong carbon strands, is bound together by a plastic resin to form a solid, lightweight structure. Carbon fiber is up to 5 times stronger than steel, yet weighs only a fifth as much. This strength-to-weight ratio is a game-changer for aviation, but the real magic lies in how composites are shaped. Unlike aluminum, which is rigid and requires complex assembly, composites are flexible before curing, allowing engineers to mold them into precise aerodynamic shapes. Picture a single carbon fiber strand next to a human hair. It's thinner, yet incredibly strong in tension. However, without resin, these fibers are like a flexible fabric, unable to hold a solid form. To create large aircraft components, Boeing developed automated tape-laying technology, where carbon fiber tape, pre-impregnated with resin, is wrapped around a mold to form massive fuselage sections. This process ensures the fibers are aligned to handle the stresses of flight, like internal pressure and bending loads. The catch? These parts must be cured in enormous ovens, a costly and complex process that requires significant investment. But the results are worth it. The 787's composite fuselage allows for higher cabin pressurization, equivalent to 6,000 feet of altitude rather than the 8,000 feet, typical of aluminum airliners. This 25% reduction in altitude, about 7.3% higher pressure, might seem minor, but it makes a noticeable difference in passenger comfort. At 8,000 feet, lower oxygen levels and bloating from expanding internal air can exacerbate jet lag. At 6,000 feet, you feel less fatigued, and as a bonus, there's less discomfort from gas expansion, a small but appreciated perk. Even more striking are the 787's massive windows, nearly twice the size of those on aluminum planes. In metal airliners, large windows create stress concentrations that, over repeated pressurization cycles, can lead to cracks and shorten the plane's lifespan. Composites, however, are immune to this fatigue, allowing Boeing to incorporate oversized windows without compromising structural integrity. These windows flood the cabin with natural light, enhancing the passenger experience. The composite fuselage also streamlines manufacturing. Traditional aluminum fuselages require 1,500 sheets and 40,000 to 50,000 rivets, creating a bumpy surface that increases drag. The 787's fuselage is a single, smooth composite piece, eliminating joints and fasteners. This reduces weight, improves aerodynamics, and lowers fuel consumption. The plane's sleek surface minimizes parasitic drag, the resistance caused by surface imperfections, making it more efficient. But the benefits of composites extend beyond the fuselage to the 787's elegant wings. The wings are a masterpiece of engineering, with carbon fiber composite spars forming the main structural backbone. These spars, shaped like I-beams to resist bending, are paired with aluminum ribs to create the wing box, a sturdy structure that also houses fuel. Composites allow the wings to flex dramatically up to 3 meters at the tips during normal flight and 7.6 meters during extreme testing without permanent deformation. This flexibility comes from the material's high elastic strain, which lets it bend 1.9% before deforming permanently, compared to less than 1% for aluminum. This property enabled Boeing to design wings with a high aspect ratio of 11, compared to 9 for its predecessor, the 767. High aspect ratio wings, long and slender like a glider's, reduce vortex drag, the energy lost when high-pressure air beneath the wing mixes with low-pressure air above it. This drag reduction boosts fuel efficiency, allowing the 787 to fly longer routes with less fuel. However, high aspect ratio wings have less internal volume for fuel, a challenge for a long-range aircraft. Boeing addressed this with a supercritical airfoil, a wing shape with a blunt leading edge and a flat top, increasing internal volume while delaying the formation of shockwaves that cause drag at high speeds. This airfoil, first tested by NASA, also improves lift at high angles of attack, reducing the risk of stall. Composites made it possible to manufacture these complex shapes precisely, using automated tape laying to create wings that deform predictably during flight, a technique called aeroelastic tailoring. This ensures the wings adapt to different speeds, optimizing efficiency throughout the flight. The 787 also tackles drag with hybrid laminar flow control, a secretive technology that reduces fuel burn by up to 30%. By drawing in slow-moving boundary layer air through tiny perforations in the tail, Boeing delays the onset of turbulent flow, which increases drag. This system, developed with NASA, uses a complex network of ducts and pumps, though details remain closely guarded. The only visible clue? Small, mysterious doors on the tail, which a patent suggests act as valves to manage airflow. This innovation underscores the 787's cutting-edge approach to efficiency. Despite its advantages, composites have drawbacks. One significant issue is galvanic corrosion, where aluminum in contact with carbon fiber corrodes rapidly due to their differing electrical properties. To avoid this, Boeing used titanium, a corrosion-resistant but expensive metal, for 15% of the plane's structure. Titanium's high cost drove Boeing to innovate further, collaborating with Norsk Titanium to develop 3D printed titanium parts. Unlike traditional machining, which wastes much of the material, Norsk's wire-based 3D printing reduces waste by 25 to 50%, and is 50 to 100 times faster than powder-based methods. These parts, the first FAA-certified 3D printed structural components, debuted on the 787, cutting costs while maintaining strength. Another challenge with composites is their poor electrical conductivity, which poses a risk during lightning strikes. Aluminum conducts electricity easily, safely dissipating lightning's energy. Composites, insulated by plastic resin, require additional protection. Early 787 wings used copper strips to guide electricity, but Boeing later removed these, relying on a nitrogen inerting system to prevent fuel tank sparks and other safeguards like sealed fasteners. While this raised concerns, Boeing insists the remaining protections are sufficient. Composites also have poor impact resistance, so aluminum is used for leading edges and engine cowlings, which are prone to bird strikes. Aluminum's ability to deform without shattering makes it ideal for these areas. The 787's efficiency extends to its desing system. Traditional planes use hot engine bleed air to melt ice, a process that wastes energy and requires heavy ducting. The 787 uses electrically heated blankets on the wing slats, powered by external ground sources or the plane's generators. This system is twice as efficient, reduces drag by eliminating exhaust vents, and simplifies maintenance. It's part of the 787's broader shift to a no-bleed air architecture, a radical departure from traditional designs.